neutron interactions with matter, basically just scattering and absorption. And then I'm going to spend most of the time talking about helium-3 tube detectors, the detection mechanism, moderation, reflection, and shielding. And then I'll just talk a little bit at the end about fission chambers and, of course, liquid simulator, because this is my baby. So, neutron interactions. So you have a target nuclei sitting here, nucleus sitting here, and you can scatter off of it. What happened? Oh, that's no good. Okay, you can scatter. Oh, my graphics is all messed up. Okay, anyway. Well, you can have elastic scattering where the neutron just goes off. You can have inelastic scattering where the neutron comes in, gets absorbed, and then the nucleus gets a little excited and spits out another neutron. And then you can have absorption, which the neutron comes in, and then the nucleus absorbs the neutron, and it gets a little excited, and then it spits out something. So that something could be a gamma, electromagnetic. It could be a charged particle like a proton, or an alpha, or a neutron. Or it could be multiple neutrons, or it could be a fission, where you get a couple of fission fragments out and a whole bunch of neutrons. That was the best part of my whole talk. So I just want to familiarize you first with some notation that we use for neutron interactions. So if you consider the interaction where you have a neutron coming in to helium-3, and then the proton goes flying out, and you end up with a triton and a proton and some kinetic energy. So a more compact way of writing this would be like so, where you have the target nucleus here, the incoming particle here, the outgoing particle, proton here, and the resultant nucleus, which is the triton there. For elastic scattering, you have a neutron coming in and a neutron going out. And in elastic scattering, you have a neutron coming in and a different neutron going out. For absorption, there's several options. You can have a neutron coming in, a gamma going out. For charged, a neutron and then some charged particle going out. And then any number of neutrons for neutral interaction, and fission is just denoted by an F, where you have the fission fragments and neutrons. So the detection technique that's used most often in this group are helium-3 tubes, or proportional counters. So you have a volume with a gas in it, and then you have essentially charged wire running down the center of it, and then the outside walls are connected to ground. So you have a high voltage difference between the central wire and the casing. And when a neutron comes in and liberates the proton and triton, they are attracted to the wire and the walls and ionized gas on the way, and they form a little electron cascade, and a pulse is collected on this wire and read out as a voltage pulse. So one thing to also keep in mind is that gammas can also produce pulses via constant scattered electrons in the gas. But these are at a much lower energy. So if this is the distribution of the pulses, voltage pulses coming out of a helium-3 tube, the gamma rays and electronic noise have very low magnitude, and then depending on where you're running the high voltage of your detectors, you will, I'm sorry, I didn't say that right, but you can see there's a plateau region here where the neutrons are sort of saturated the cascade, and so you want to operate your detector in this region. The electronics, pulse processing, I was going to bring a little Amtech circuit in, but I forgot it, so you could look at it. But basically, the electronics takes this pulse coming out of the detector and picks it off from the high voltage line, sets a discriminator to discriminate pulses of interest, and then once the discriminator triggers on a pulse, it outputs a logic TTL pulse. So one thing to keep in mind for neutron detectors, unlike gamma detectors, all neutrons look the same. So you're just interested in the number of neutrons, and you're not interested in the magnitude of pulses for the helium-3.
So if you could go back 2 slides. What looks like a peak in that chart there, is that meant to represent the Geiger region that you would reach if you turned up the voltage even more?
Yeah.
Okay.
So the helium-3 counters are most sensitive to thermal neutrons, so neutrons at very low energy. Fission neutrons are produced at 2 MeV, so one needs to moderate this energy down to the thermal region. And so again, my graphics didn't work, but and the way this is done is simply by transferring the momentum of the neutron to protons. So the neutron comes in, and since they are similar masses, just like billiards, the proton and the neutron go off with roughly half the energy of the incident neutron. And one of the most effective ways of doing this is using polyethylene, which has loaded lots of protons.
When that happens, the hydrogen remains as part of the molecule that it was originally in, correct? Or is the proton knocked out?
I don't know. Is it knocked out? No. I don't think so. It just jiggles? Yeah. Okay, thanks.
We are allowed to ask questions.
Yeah, please do. You got an hour to fill. John?
Something might get knocked out because of neutron damage. As a chemist, I like to suggest a different way of writing the polyethylene. N times CH2 into the CH2 parentheses N.
Okay.
Infinity.
Okay. I stole this from Jim Stewart, so I can blame him. So if you've ever been involved in any of the fundamental schools or the IAEA schools, there's a little experiment that we always do to get the students familiarized with a feeling for how much moderation you need in this detector. So the basic experimental setup, you have 2 helium-3 tubes encased in polyethylene and a fast neutron source like a emerging lithium or a californium source. And then you vary the thickness of the polyethylene and look at the counting rate that you get out of the helium-3 tube. And you find that at some point it reaches a maximum, and then you start losing neutrons, and it starts to come down again. So the typical detector is actually slightly under-moderated because if you can always add moderation, and you can also have moderation in a sample that you're interested in, so it's better to under-moderate than to over-moderate. So you can also use reflection off of large nuclei to enhance your counting rate if you want to scatter more neutrons into your detector. Nickel is often used as a reflector, but other high Z materials will work as well. Cadmium can be used for shielding. Cadmium absorbs thermal neutrons, however, fast neutrons will more likely scatter off of it. So if you want to use cadmium as a shielding, you need to combine it with the poly to moderate the neutrons before they come to the cadmium. So here's an example of a typical neutron well counter. You have several helium-3 tubes surrounding a sample cavity, and they are embedded in polyethylene. So if you say we're in a high radiation environment, you might consider doing something like putting a layer of cadmium and then some poly on the outside of this, so that neutrons coming in from the outside will go into the poly, slow down, and then get stuck in the cadmium and never make it to your detector hole. Also, if you have a, well, I won't go into scattering right now. So fission chambers are just another variation on these types of gas detectors. Basically what you have is you have a thin layer of U-235 on the inside surface of the gas volume, and neutrons will then induce fissions in the U-235. Then the fissions ionize the gas, which is typically argon with some methane. And because the fission fragments have a larger ionization potential, you can operate these at a lower voltage. And because of the large signal that you get from fragments, you also are less sensitive to gammas. And so this is particularly useful for spent fuel assay. In fact, I think it's the only way that we have of assaying spent fuel right now. So liquid simulators also can be used to detect neutrons. Sorry, I'm just upset about my graphics. So a neutron, they're sensitive to neutrons. The neutrons come in and they pass their momentum to a proton, and then the proton then goes shooting off and produces scintillation light, which then can be collected on a photomultiplier tube and read out. Unfortunately, gammas can do the same thing by coming in and scattering off an electron. So there's the neutron, there's the gamma. Okay. Fortunately, the pulse shapes that you read out of the photomultiplier tubes are different, and you can separate the pulses either by taking the pulse and digitizing it, and then just doing a chi-squared comparison to some template pulses that you have. Or you can integrate the pulses, and you can see that the gammas have a much quicker rise time than the neutron pulses. So if you look at a short integration window compared to a longer integration window, that ratio for the gammas will be much higher than for the neutrons, and you can use that to discriminate between the pulses. So a possible liquid simulator counter might look something like this, where you have, instead of helium-3 tubes around the well, you now have a liquid simulator, and then some light guide directing the light into both multiplier tubes on either end. One of the advantages of this, which will come up later when we start talking about coincidence counting and multiplicity, is you're detecting fast neutrons in this case, so you can be less sensitive to accidental coincidences. And that's pretty much all I have. I'm sorry. Questions?
much do these cost for achieving 20 to 30% with liquid scintillators? How does that compare to the cost of achieving 20 to 30% efficiency with the other three tubes?
It costs a lot more. It would cost I think we sort of estimate roughly once the R&D is done to design the detector and everything, you could build one for something like $500,000 or maybe less. But the advantage is that, well, we actually had hoped to use these for highly enriched uranium, so you can cut out some of the americium lithium neutrons, because you're looking at fast neutrons, and so you have some information about the energy spectrum. You don't have really great resolution, but you can at least cut out some of the lower energy interrogation neutrons. And also your gate width is like, so your die-away time is less than 100 nanoseconds. So you can increase your triple efficiency.
What's Ne213? Is that the name of the liquid, or?
That's the liquid scintillator. I don't know what. It's BC1501 if you get it from Vicon, and it's the same thing, and I don't know what it stands for. But it's mostly, I think it's pretty much boron, so it is.
What's the energy distribution of those photons look like?
So the fission distribution is peaked around 2.
No, I mean the photons from the...
Oh, the photons going into the...
The photon coming out of the scintillator.
Right.
They're proportional. Oh, you mean what's the... Wait, well, they come at once, so you sum, so you're summing them, so you see, so you get a voltage pulse out of your PNT.
Right, before PNT, I'm talking about the photons before we reach.
What's the wavelength of the photon?
The wavelength range, yeah, what's the color of this?
Oh, it's not UV.
It's visible. Is it a different rainbow color, or?
I don't know.
But this is liquid.
Okay, right.
That makes sense.
Or is it concentrated on the high energy region?
It's not, I'm pretty sure it's not concentrated on high energy. But I don't know.
I got a question about the previous question about radiation damage from the neutrons. I think on the polyethylene, I think we do have radiation damage, but just the fact that the atomic density of the solid poly is so much greater than the neutron source strength, such that it's negligible. That's why we don't see the poly being rid of right away. But
plenty of molecules to be damaged.
Right.
Still can affect it. But this would avoid that problem. Right? This is different.
Kirill just came up with another neutron detection technique, and we ought to add that to this list as well, is lithium detectors.
Yeah.
I don't know if I even remember the basics of how those work.
Is it just lithium-6?
P1 should be able to answer that question.
Yeah, after all, it's my dissertation topic. Basically, the source neutrons are thermalized by the block of poly around the shell.
That make up the wall of the shell.
Right, and then lithium is kind of plated onto the metallized surface. And then you have thermalized neutrons interacting with lithium-6 layer, and you have triton and alpha particles coming out of that interaction. And then those primary charge particles are ionizing the field gas molecules or atoms. Then those secondary charges are the your signal carriers. It's gas detectors.
And I believe that is, the major advantages of that are high volume of detector at low cost. Is that the main?
Mm-hmm.
What's the diode type on that?
Diode?
Yeah.
Well, I mean, it's gas.
Yeah, but everything's gas. So I thought one of the
It's not
big
gas.
benefits of this is that the diode times are so short that you can handle really high count rates. And then that thermal neutron counter was the first step in this direction by reducing your gate width significantly so your multiplicity efficiency could go up. And so you guys maybe don't have to worry about count rates. Well, is that type of detector intended for use in coincidence or multiplicity counters, or is it primarily intended just for essentially as a big frisker?
Yeah, just
for yes, no,
right. But it's a gas detector, so depending on your dimension of how long you expect the electrons to travel, which are the main signal carriers, you have different diode times for signal.
Well, the other factor will be how thick the poly is, because a big piece of the multiplicity counter's die-away time is how long the neutron spends wandering around the detector before it hits a helium-3 tube and generates a signal.